Okay, incredible question here. I mean, it's relatively normal until we get to part C, and then it's a little bit different than I've ever seen before, but a lovely, well, we'll see in a minute. Okay, first up, normal stuff. We need to differentiate an exponential. Going to use the chain rule. Differentiate the outside, which just gives me e to the x cubed minus 2x. That's how we differentiate e. It just stays the same. And then times by the derivative of the inside. 3x squared minus 2. Of course, you can do it by letting u equal x cubed minus 2x, doing dy by dx equals dy by du by dx, but this is the quicker way to do it. Also, just pay attention to the fact that we've been asked to do that. It's quite possible that's going to be useful later on. Next up, we're given a couple of functions, g and h. Notice they're defined over all real numbers, but x is greater than 0. Find the x coordinates of the points of intersection. So that's going to be when they're equal, when the y values are equal. So when 8x cubed e to the x cubed minus 2x is equal to 3x to the 5 plus 4x times e to the x cubed minus 2x. Now this is always going to be greater than 0, as is this. It's on both sides, so I can divide through by it. And I've suddenly got just a polynomial in x, albeit it's got order 5. 3x to the 5 minus 8x cubed plus 4x is equal to 0. And there's a common factor of x, so we can take that out, which leaves us to be what looks like a hidden quadratic. We can also divide through by x, by the way, because remember the function is only defined for x greater than 0, so we can cancel that out. Or you could say that x equals 0 as a solution and then reject it. Okay, let's try and factorize this. So if it's going to factorize, we're going to have a 3x squared term and an x squared term. In this hidden quadratic, you could, of course, let u equal x squared and create the quadratic 3u squared minus 8u plus 4, if that helps. But I'm just going to go straight for it and factorize in terms of x squared. I've got a plus 4, I've got a minus here, so they're going to have to both be minuses. And if we go with 2 and 2, that works. We get minus 6x squared minus 2x squared gives us minus 8x squared. So therefore, 3x squared is equal to 2, or x squared is 2/3, or x squared equals 2. And that means that x is going to be the square root of 2 over 3, or the square root of 2. Ignore the negatives again, because x negatives, since x is greater than 0. These are x coordinates of the points of intersection. This leaves us with part C, the hardest but the best part. So we're told that C1 lies above C2 between these 2 points of intersection. Let me, therefore, I'll put C1 looking, we don't know what it looks like, but it's just to kind of demonstrate C1 there, and then C2 is going to be like that. And we're asked to find the region bounded between the curves, so this here. Points of intersection, remember we found in the previous part, root 2 over 3, that's going to be the smaller one, and then the square root of 2. So my area is going to equal the integral from this lower limit to the higher limit. And then I want to find like the whole area underneath C1, which is going to be 8x cubed times e to the x cubed minus 2x. And I need to minus the other function, which was 3x to the 5 plus 4x. by that exponential. This exponential is what makes this tricky. And of course, we can bring this together. So that is the two areas separate, but you can just bring the integral together. So we've got 8x cubed minus 3x to the 5 minus 4x times e to the x cubed minus 2x dx. So some things that ran through my head at this point is, okay, could we do a substitution? But if we did a substitution, you'd have to change the limits, which isn't going to be particularly nice. And, of course, if we had like the derivative of this here, then fine, you can do a substitution or inspection, but substitution is not going to help basically. Um, so where does that leave us? Not many places, except what about integration by parts? Now, what we definitely don't want to do is start integrating this. This can't be integrated exactly, I don't think. But then if you differentiate this, sorry, if you then differentiate this, as we've seen from part A, it's going to get more complicated. But that part A, I did talk about it. I said, like, don't forget about it. We've got the derivative of e to the x cubed minus 2x. So what if I could get that as one of my functions in the integration by parts? Could we somehow factorize out a 3x squared minus 2? And you can actually, it turns out. So what I didn't quite see it, to be honest. I decided to do a polynomial division. Let's just see what happens when I divide 8x cubed minus 3x to the 5 minus 4x by this 3x squared minus 2. Oh, and I need to write it now in order of powers. So minus 3x to the 5 plus 0x to the 4 plus 8x cubed plus 0x squared minus 4x plus 0. Okay, minus 3x to the 5 divided by 3x squared is going to give minus x cubed. Multiply back through, get plus 2x cubed here. No x to the 4 term actually needed. Minus it, leaving us 6x cubed. Divide 6x cubed by 3x squared, gives us plus 2x. Multiply back through. Actually, it divides into it. So it turns out that we can write this thing here as 3x squared minus 2 multiplied by minus x cubed plus 2x. So you might have been able to factorize that straight away. Fair play if you can. I didn't see it myself. Polynomial division works really well. In the answers, they actually take the minus out. You can factorize a minus out of the whole integral, and then you end up with a positive x to the 5. That does make life a little bit easier, but I'm just going to stick with it for now as I've done it. Okay, so my next line is going to be the same integral, but I want to put this bit together. So you know what? I'm going to write it first. No, I'm not. I'm going to write the remaining bit first. So I've got 2x minus x cubed multiplied by 3x squared minus 2 times e to the x cubed minus 2x. Because I now know what the integral of this is. So this is going to be my v dash. Suddenly it's all coming together. This is going to be my u. So v is simply e to the x cubed minus 2x. Brilliant. U dash is then 2 minus 3x squared. Applying integration by parts, we have uv in brackets, root 2 over 3, minus the integral of u dash v, respect to x. Let's substitute that in. We're going to get 2x minus x cubed multiplied by v, which is e to the x cubed minus 2x, evaluated in these limits, minus the integral of, it was u dash v, so that's 2 minus 3x squared times e to the x cubed minus 2x. But looking at this one, it's basically this one again, except the negative, 3x squared minus 2. So what I can do is actually make that positive, and then make that positive and minus, and this integral is simply, oh, sorry, I forgot to put the limits in, going to be e to the x cubed minus 2x, evaluated between root 2 and root 2 over 3. So we're there. Amazing. Like by using this idea of, we had this horrible integral, brought it together, factorized it, realized that the derivative was in there, and then did integration by parts, and then got the nice thing about this one is that in the second integral, we get the derivative of e to the x cubed minus 2x, and therefore we've done the integral. Just need to substitute in the limits. So first up, 2 root 2 minus, now when we cube root 2, we actually get 2 root 2. So this first term is just going to be 0. I can ignore it. And I'm going to minus 2 times the square root of 2 over 3 minus, now when I cube the square root of 2 over 3, I'm going to get 2/3 times square root of 2 over 3. Because like when you cube x, the square root of x, then you're going to get root x times root x, which is x times root x. That's what I'm using here. And then I'm going to be times in by e, so I run out of space, to the x cubed. It's very similar. I'm just going to get 2/3 times root 2 over 3 minus 2 root 2 over 3. So that is that first one, and then I'm going to be adding this thing here. So e to the 2 root 2 minus 2 root 2, then minusing e to the 2/3 root 2/3 minus 2 times root 2/3. Okay, it's quite a lot going on here. Let's bring it together. So 2 can be written as 6 over 3, meaning that I'll get 6 over 3 lots of root 2/3 minus 2 over 3 lots of 2/3. That's going to be 4 over 3 lots. But then I've got a minus there, so it's going to be minus 4/3 root 2/3 e. And very similar over here, I can replace this by 6 over 3. So e to the minus 4/3 root 2 over 3. This actually just becomes 0, so then I'm going to actually be adding 1. And then I'll be minusing e in a similar way. This is 6 over 3 e to the minus 4 over 3 root 2 over 3. We're nearly there. So this can be written as 1 minus, I can factorize out the e to the minus 4 over 3 root 2/3. And inside the bracket, I'm going to have 1 plus 4 over 3. And that is in the required form. We're all the way up here, a plus b e to the c. So I actually left my answer like this. I didn't put the plus in. You could simplify it a little bit more. We could rationalize the denominator and put things over a common factor. So an alternative is to write 1 minus, and then I can, um, sorry, I missed something out there. I forgot my bad. That should have been root 2/3 there. I forgot that term. Okay, that's better now. That works. Right, or we can rationalize the denominator times top and bottom by root 3, giving 9 at the bottom, put it all over a common factor of 9. So I'll get 9 plus 4 root 6 over 9. That is the same thing. And then e to the minus, and again, times top and bottom by root 3, 4 root 6 over 9. Slightly neater, I think. So lovely question. Well done. Yes, good.